So in the previous class, we had seen that there was a necessity of changing from the Lagrangian from psi dagger psi to psi bar psi, because this object is not invariant under Lorentz transformation while this object is. This happened precisely because the transformation generated by matrices d lambda for Lorentz transformation are not unitary. That means d dagger, d lambda are not unitary, are not identity. So therefore, I cannot use psi bar psi or psi dagger psi as a invariant object in the Lagrangian. Remember, the Lagrangian which we proposed initially was something like psi dagger I h bar gamma mu del mu psi minus mc psi. So this kind of Lagrangian we thought would do our job of giving rise to the Dirac equation, which it does. Variation with respect to psi dagger indeed gives rise to the Dirac equation, but unfortunately the piece psi dagger psi which is appearing with a mass over here is not Lorentz invariant. So we realized that we should not be using psi dagger psi, but we should use psi bar psi rather. So psi bar psi, where psi bar is related to psi dagger through extra gamma naught multiplication. So if that is the proposition, we should check whether this kinetic term is invariant now under Lorentz transformation or not. And indeed, we will see that it is invariant under Lorentz transformation if the thing which is appearing inside. So we try to see how does it transform. Inside there are things which appeared like that. So you see d dagger, gamma naught, gamma mu, gamma inverse of nu mu. So all these things will appear if I try to do Lorentz transformation. Psi will transform with a d, del mu will transform with a lambda inverse, gamma mu is a matrix, psi bar will transform with a d dagger gamma naught. So putting all these things together, I will get a d dagger gamma naught, gamma mu, lambda inverse, and the d. All the items which will be generated from Lorentz transformation. Now, it so happens that this object inside which appears ultimately d inverse gamma mu d lambda transforms gamma mu as a normal vector would have done. Gamma mu is not a normal vector. It does not have 4 components as a real numbers. A normal vector has 4 components as real numbers. Gamma mu are 4 matrices. So all its 4 components are 4 matrices. So therefore, it is not very straightforward that it will transform as a usual normal vector. But a matrix transforms under Lorentz transformation as a similarity sort of transformation where you multiply d inverse and d from the left and the right. The end result happens to be that it almost transforms like that it is a normal vector. Forgetting about its matrix structure, gamma mu transforms indeed like a normal vector. Only catch is that gamma mu are matrix objects, not real numbers. So once this happens, if this happens, then you can see what is happening inside. Inside, if this transforms as a gamma mu nu, and outside there is a lambda inverse. This lambda inverse and this lambda cancel each other, and the object will become invariant under Lorentz transformation. So that is the goal we were looking to set. So the essential criteria for that happening was this, that the gamma mu transforms almost like a normal vector. In order to see whether this happens or not, we started doing the computation of the left hand side explicitly. I'm going to write d inverse this way and d as this. Why can I write that? Because you knew that d, the transformation matrix, can be written as an exponential iota omega alpha beta s alpha beta, depending upon where you observe iota, whether s contains iota or not. In this notation, it doesn't matter. Ultimately, the similar kind of structure will be set up whatever notation you use. So I'm using a definition where iota right now is kept on the outside. Previously, we had done business with iota, what was absorbed in the definitions of S as well. Both of these things are equivalent as discussed previously as well. So go ahead, do this computation, collect various matrices. One matrix multiplication will be this identity coming with this gamma mu and this identity. So there will be gamma mu like this. Another term would be this multiplying with this and the identity. That will be the first term of the commutator. Similarly, this identity multiplying the gamma mu over here and then combining with this will give me the second term of the commutator. And ultimately, you will get these kind of things under the multiplication of both sides. Now, there is a non-trivial claim which I am going to propose, which was the commutator of S alpha beta, which is the generators of the Lorentz transformation for spinors, and gamma matrices, ultimately is proportional to gamma matrices back and a matrix which is multiplying, which is now a generator of Lorentz transformation for vectors. S were the generators of Lorentz transformations for spinors. M is the generators of Lorentz transformation for vectors. These are the M's, the 6 M's, 3 rotations and 3 boosts. You see 3 boosts here and 3 rotations are in the red. So you can see this is the claim I am making. The commutator between S and gamma gives me a result proportional to gamma and M. M is the generator of the vector Lorentz transformations. If this happens, then you can see that again the whole expansion adopts a form of a exponential. These are the different terms appearing in the expansion of the exponential, and ultimately it will become exponential iota omega alpha beta. This time m alpha beta will appear because of the commutators being converted into m. You see in the expansion commutator second power, commutator third powers, and so on and so forth will appear. And if commutator of S and gamma is m, ultimately m square, mq kind of things will appear, and this will become exponential of omega times m. 6 omegas and 6m multiplied together and then exponentiated. And remember, this was just the vector transformation lambda. So therefore, the end result will be lambda mu nu gamma nu. So this result is indeed true, subject to the condition I can prove that the commutator between S and gamma becomes multiplication between m and gamma. So nu gets summed over. You see nu is getting repeated. No other index is repeated in one complete term. So S alpha beta, 2 index from here and 1 index from here appear in the following way. The first 2 index decide which m alpha beta I am going to talk about of the 6. And the mu over here is going to talk about which row of the m alpha beta I am going to talk about. So I'm going to prove this now with a couple of examples, and then we will be having a faith upon this commutator turning into this m times gamma. So this will become true. Therefore, this will become true. This will also become true, and hence the piece which is the kinetic term will become invariant. So that is what we are going to see with the help of certain examples. Okay. So let us work it out and see whether we get the claimed identity or not. So the thing which we are trying to chase is whether S alpha beta gamma mu commutator indeed becomes multiplication of F alpha beta, M alpha beta and gamma nu, where the row, muth row, this decides the row, and the column, this is muth column rather, and nu is being summed over. Along the row you sum. Nu 0, 0, 1, 1, 2, 2, 3, 3, and so on. So let us try to see whether this emerges out or not. So I'm going to think of a Lorentz transformation which is perfectly boost-like. So I'm going to do a Lorentz transformation which is just a boost along the x-axis. That means all other parameters are 0. Only boost along x-axis parameter is non-zero. I'm going to choose that parameter omega 0, 1, which is 1. And being antisymmetric, it is also equal to minus of omega 1, 0. And all other parameters are 0. Boost along y-axis is not being done. Boost along z-axis is not being done. Rotation along any of the x, y, z-axis is not being done. So omega mu nu is equal to 0 for all mu nu which are not equal to 0, 1. Okay, only omega 0, 1 and omega 1, 0 are non-zero. All other omega mu news are 0. So therefore, the D matrix, which transforms the spinors, which was being written as exponential of iota omega mu nu s mu nu, this will become equal to exponential of iota omega 0, 1, which is 1, and s 0, 1. That's all. Okay. Now, if that is the case, ultimately the claim identity which we are going to look at should have a S01 gamma mu should be equal to M01 mu nu and gamma nu. This is what should emerge out under this Lorentz transformation. So that means I have to choose 4 mu's differently. I can choose mu is equal to 0, 1, 2, 3, and correspondingly right hand side will have here 0, 1 or 2 or 3. So let us do one example for mu is equal to 0. That means I want to evaluate what is the commutator between S01 and gamma 0. Result says the result, looking at the result, it looks like the commutator should emerge out to be M01 0 nu. This should be the claimed result. Let us verify whether we do get this result back or not. So let us write down the S01 matrix. S01 matrix is half of gamma 0, gamma 1, because that is the generator. Gamma 0 is just appearing over here, and then let us do this multiplication, opening up the commutator. If I open up the commutator, I will get 2 terms, gamma 0, gamma 1, gamma 0, which is the first term, and gamma 0, gamma 0, gamma 1, which is the second term. Now two gamma zeros are appearing over here, which will make gamma naught square, gamma 0 square, and we all know gamma 0 square is identity. So therefore the second term will just become minus of gamma 1, minus of gamma 1. Look at the first term, which is gamma 0, gamma 1, gamma 0, gamma 0, gamma 1, gamma 0. And we also know that gamma 1, gamma 0 over here is negative of minus of gamma naught, gamma 1. So this is equal to minus of gamma naught, gamma 1. And again, gamma naught is identity. So this first term is also minus of gamma 1. So half of minus of twice of gamma 1 is equivalent to minus of gamma 1. This is the left hand side. Let us check what do we get on the right hand side. Right hand side, if this identity is true, I should get, so sorry, I am supposed to get a minus over here. Look at this previous result. Here when I wrote down the commutator, it became m up to a negative sign change. So the claim result is that commutator is negative of m. So that is what we are trying to do. Now let us find out this object over here and see whether it is negative of gamma minus gamma 1 or not. M01, this is the row which is 0th. This is the column which is row 0, and nu gets summed over the first entry, second entry, third entry, and fourth entry. So M01 along this row has only one non-zero element, which is M01. So when I sum over nu will take value 0, 0, 1, 1, 2, 2, 3, 3. Out of these 4 entries, only M01, 0, 1 is surviving. M01, 0, 1 is surviving because M01 matrix is this. So in this summation, only one term is going to survive with value 1, and this will become gamma 1. So indeed, it is negative of the commutator. So S01 gamma 0 is indeed negative of minus M01 0 nu gamma nu. So at least we have verified for this pair 0, 1 and mu is equal to 0, it works out. If you can do another example, you can take S01 gamma 1 here. You will again find out that it is indeed coming out to be true that S01 gamma 1 is indeed negative of minus M01 1 nu and summation over gamma nu. And actually you can keep doing these exercises for different values of alpha, beta, and mu. If you take alpha is equal to 2, beta is equal to 3, gamma is equal, mu is equal to 0, you will get M23 0 nu and summation over mu. And similarly, if you take 2 3 1, you will get 2 3 1 nu and summation over nu. You can verify for all of the terms you are indeed getting this structure. So the claim which we are going to prove indeed turns out to be verified, and we have not proven but verified this, that put together we have a general structure that you take any of the S mu nu and you take any of the gamma matrix, you will get the mu nu will identify which M we are talking about. The component of the gamma will tell me the upper index of that M, and the lower index will be summed over. So indeed, this structure emerges out, which we assumed. If that emerges out, that means the reverse map which we had talked about will work fine. That if the claim identity is true, then this commutator over here with a minus sign will be replaced by a positive of generator M for vectors, and higher commutators, square of commutators will be squares of m's and whatnot. Ultimately will become exponential of omega times m, which is the vector transformation matrix. So therefore d inverse gamma times d gives you back lambda times gamma, which was the claimed result which we are trying to obtain. And once that happens, we can now see that the kinetic term is also invariant under Lorentz transformation. So now we have a good Lagrangian. So as we can see, kinetic term, the d inverse gamma, mu and d which was appearing now has been written in terms of this lambda, the lambda, mu alpha, gamma alpha, which is this lambda, mu alpha, gamma alpha, and already there was a lambda inverse nu mu which was coming from the transformation of the partial derivative. This and this, they are just numbers, they are not matrices, they are component of matrices. They can combine and give you a Kronecker delta mu alpha, because they are the matrices are inverses of each other. That means components multiply to each other such that the row of one combines with the column of other and so on, gives you a identity matrix. That means the component becomes the Kronecker delta. Unless they are the same, they will give you 0. If they are the same, they will give you 1. So once you identify that mu over here which was appearing has to be summed over with mu appearing over here, that mu gets transformed to lambda inverses lower index. So this mu and the upper index here are getting summed over, therefore you will get a Kronecker delta. This is the inverse transformation matrix which we had written. Once the Kronecker delta appears, it will make the nu appearing over here to the value alpha. So ultimately, or you can say that it will make alpha appearing here taking the value nu. So ultimately the end result will be this index here and this index here will become same. That is the Einstein summation coefficient. So these two are being summed over, and the left hand side was also the same structure. So it is invariant. This has become nu, but nu is being summed over, right? Similarly, here mu was written, but mu was summed over. So there are 4 summation term and there are 4 summation term which are exactly the same. So this nu here is a fictitious dummy index which is summed over. You could have written this after the end of the day mu as well. So therefore the kinetic term is also invariant. The mass term which we had written is also invariant now, and therefore the whole Lagrangian, which now we can write as psi bar, the kinetic term and the mass term together, is an invariant Lagrangian under Lorentz transformation. Okay, so once we have a valid Lagrangian at our hand, again we will do the similar exercise which we had done for the scalar field. First we will try to go to the phase space of this. So remember, in this case we have complex field, not real field. Psi is a complex. Psi had, first of all, it is a column matrix. So it has psi 1, psi 2, psi 3, psi 4, which we had collected in terms of phi naught and chi naught, if you remember. But anyway, so these are complex entries, so they are not real. So therefore, psi bar appearing over here in hides a psi dagger, which is not equal to psi, because it is not a real scalar field. It is a complex spinor field. So it has real entries and imaginary entries in the psi. So either you can treat collection of psi as a collection of four complex fields, psi1, psi2, psi3, psi4, that has a four real parts and four imaginary parts, or equivalently you can think of the whole thing as a four complex psi and four complex psi dagger. So this is what one can do the business with. That you will say that real part or imaginary part are independent fields, or you can say that psi and psi dagger are independent fields. Both of them are equivalent. Now, if I try to do this, we will take this Lagrangian, and first I will try to find out the momenta corresponding to the field psi. Remember, there are 8 fields ultimately. Real part of psi1, real part of psi2, real part of psi3, real part of psi4, imaginary part of psi1, imaginary part of psi2, imaginary part of psi3, imaginary part of psi4. Equivalent description are 4 complex field psi and 4 complex field psi dagger. Okay, so this is how we can do the business. So if we can define either the real part as a 4 collection and the imaginary part of 4 collection, or psi and psi dagger as 2 separate fields. So first I obtain the momentum corresponding to psi. Momentum corresponding to psi, that means any component of psi you take, its momentum corresponding to that would be psi dot. Okay, del psi dot, this object. That means it has 4 components, take any of them. Psi1 dot, it will try to look in the Lagrangian and find out where is psi1 dot hiding. So this psi and this psi bar together will generate number. Psi bar will be psi1 dagger, psi2 dagger, this will become a star after taking dagger, and row will become a column will become a row rather. So psi3 star, psi4 star, and then there will be a gamma 0 which is under dagger, get back to itself, and then this iota times gamma mu derivatives of psi, derivatives of iota times gamma 0, derivatives of psi will be psi1 dot, psi2 dot, psi3 dot, psi4 dot. So you will see after all the multiplication, there will be term which will be psi1 star going to psi1 dot, psi1 star with multiplication of these things in between, giving you identity. Actually, it will not do anything. Iota can be taken out, gamma naught square is independent. So therefore, psi2 star will get multiplied with psi2 dot, psi3 star will get multiplied to psi3 dot, and so on and so forth. So that means whenever I take del L upon del psi1 dot, I will get iota times psi1 star. Similarly, for psi2 dot, I will get iota times psi2 star. Psi3 dot, I will get iota times psi3 star, and so on. Collectively, I can write if I write then down the psi dagger, psi dot, the end result would be psi dagger, because psi dagger is component psi1 star, psi2 star, psi3 star, psi4 star. So put 1 here, you will pick this one. Pick 2, put 2 here, you will pick the second one. So all the stars appearing over here can collectively be written as a dagger. Okay. So therefore, I will have a momenta corresponding to psi will be obtained as iota times psi dagger. So psi and psi dagger were supposed to be independent fields as we discussed. However, they happen to be related in the phase space. In the phase space of the theory, they are conjugate to each other. This is momenta of psi. Okay, and in this way I have written nowhere the derivatives of psi stars are appearing, only the derivatives of psi are appearing. Psi daggers star is not appearing anywhere. So if I compute the momenta corresponding to del L upon del psi dagger star, I'm going to get 0. There is no momenta corresponding to this in the way we have written the Lagrangian. There is another cliched way of writing the same thing as a product of the derivative action hitting this term and a total derivative term. So those things I'm not going to discuss in this course because this is not relevant for us. But the way we are writing the Lagrangian, which is consistent with Lorentz transformation, I'm going to get the momenta corresponding to psi is psi dagger with iota, However, the momenta corresponding to psi dagger itself is 0 because there is no psi dagger star appearing in the Lagrangian the way we have written. So therefore, the total Hamiltonian density which we should be obtaining in phase space should be summation over all the p momenta pi's and all the dynamical variables dot minus L. In this case, only one set of momenta survives, which are the psi daggers times iota, which are the derivatives of psi dot. Psi dagger dot does not appear, its momenta does not appear, so therefore that pair will not appear in this summation. So ultimately only psi dot, its momenta will be there, and the Lagrangian, which can be written like that. So you see that the Lagrangian over here has become a nice structure in which only thing of interest, you can see that the psi dot appearing from the first term gets exactly cancelled from the first term of the Lagrangian. So psi dot terms gets wiped out under this computation. Only spatial derivative terms survive. So this has 4 terms: gamma 0, del 0, gamma 1, del 1, gamma 2, del 2, gamma 3, del 3. Out of this, gamma 0, del 0 term exactly cancels this, because this psi bar also has a gamma 0. So gamma 0 becomes identity, and these two terms exactly cancel each other for mu is equal to 0. So only thing which survives, not only the three things which survive are the three spatial derivatives. The temporal derivative gets exactly cancelled out, spatial derivatives survive with respective gamma, and the mass term survives with a positive sign, because Lagrangian was taken out with a minus sign. In the Lagrangian already the mass term was coming with a minus sign, so ultimately it becomes plus. So overall, the Hamiltonian density is psi dagger, spatial derivatives with appropriate gamma naught and gamma I multiplication with a minus iota factor, and the mass term with a gamma naught factor, and then a psi back. So you see, this is a column matrix, this is a row matrix. Inside there are certain matrices. So ultimately, you are going to get a number. The Hamiltonian density has to be a number. Lagrangian density has to be a number. And once I integrate the Hamiltonian density over all space, I will get the total Hamiltonian, just like we did for scalar field as well. So starting with a consistent Lagrangian for Lorentz transformation, I am able to generate, or write down rather, not generate, write down the Hamiltonian for a Dirac system. This does not look like very much like a harmonic oscillator thing which we obtained for the scalar field, but we will soon see that indeed it is hiding a harmonic oscillator structure, and therefore we can use the harmonic oscillator quantization techniques which we had learned previously as well. So in order to see that, let us do certain algebraic manipulation and massaging to the equation, and then we will see how the oscillator structure emerges out naturally. So look at again the Dirac equation, the variation of the Lagrangian with respect to psi dagger or psi bar is going to give me this Dirac equation. Here now on I am putting C is equal to 1 and H bar is equal to 1, because I have to maintain the C and H bars at so many places. So this is the natural units in which things are written. You know that whenever I'm writing M here, it should have been MC, and somewhere H bar should also be appearing because of the derivative version of the momenta which I had written. But anyway, right now I'm just putting them to 1 for just for convenience. Looking at their mass dimension, we will be able to settle where C is appearing, where H bar, and where their combinations are appearing. So this gives us a nice structure to look at. Mu is getting summed over in the Dirac equation. Remember, in the Hamiltonian, the 0th part has been cancelled. The summation is only over ith part. But in the equations of motion, all the 4 mu's are appearing. So let us look at the equations of motion. What I do, I take the whole equation, which is a matrix equation multiplying a 4 cross 1 matrix. So this gamma mu is a 4 cross 1 matrix. This gamma mu is rather 4 cross 4 matrix. This psi is a 4 cross 1 matrix. This M is hiding an identity in between. So ultimately it is again 4 cross 4 multiplying of 4 cross 1. So overall structure of this equation is some matrix which is a combination of all the derivatives and gamma mu put together acting on psi, and some M multiplied with identity acting on psi. So ultimately I will get a 4 cross 4 dimensional matrix multiplying a 4 cross 1 dimensional vector, and that should be 0. This is the equation telling you. What I do, I multiply the whole equation with another matrix. Which another matrix? I take this minus iota gamma alpha del alpha. Again, alpha is being summed over. That means I will take gamma 0 del 0 plus gamma 1 del 1, gamma 2 del 2, gamma 3 del 3. So I take this matrix, which is in its expanded form, iota, which is coming from here, gamma 0, the derivative with respect to time, gamma 1, which will be sigma 1 minus sigma 1 here, delta 1, gamma 2, which will be sigma 2 minus sigma 2 and gamma 2, delta 2, gamma 3, which will be sigma 3 minus sigma 3 and delta 3. Collectively, I am writing sigma I minus sigma I and delta I. Again, I has to be summed over. This is just a notational version of the full expansion. So that matrix I take and multiply this matrix equation of motion. So I take the whole thing, the equation of motion, multiply it through this matrix. Okay. Ultimately, this solution which I'm going to multiply it through will be matrix multiplication. This matrix multiplying this equation, this whole thing equation of motion is some 4 cross 1 dimensional matrix at the end of the day, because 4 cross 4 multiplying a 4 cross 1 should give me a 4 cross 1, which should be a 0 matrix, but ultimately this left multiplication is some 4 cross 4 multiplying in 4 cross 1 already, and to that I'm going to multiply this whole object, which is this. Okay, so this is the mathematical formal structure. So let us see it cleanly. What do I get? So I have this equation at hand. I multiply this equation with this object, and let us see what are the different terms I'm going to get. The first term becomes this, an extra multiplication with gamma alpha del alpha, and the second term also becomes m times multiplication with minus iota gamma alpha del alpha. So minus term, which was already appearing in the equation of motion, becomes a plus over here, and ultimately I have these two terms, which is fine. This iota can be pulled out, multiply with this minus iota, becomes plus 1, and then I have a gamma alpha and the derivative. The derivative will go across because gamma mu matrices, none of the gamma matrices have any space-time dependence. So the derivatives will just go through, and I can collect all the derivatives on one side and all the gamma matrices on the other side. But in this, order matters. First I have a gamma alpha and then gamma mu. I cannot write it as gamma mu, gamma alpha, whichever way I want, because these are matrices. Two matrices A and B cannot be written B and A unless they commute. And I know gamma alpha, gamma betas do not commute. So I will be attentive to the fact, and I will write the order right. That gamma alpha first appears and then gamma mu appears. The derivatives can be written in any way because they are not matrices. They are just operational partial derivatives, and partial derivatives commute with each other. So that is fine. The second thing which is appearing over here, C iota times gamma alpha del alpha psi should be equal to m of psi already, because of the equations of motion. Iota times gamma mu del mu psi, where mu is summed over, is equal to m psi. So therefore the term appearing over here, which is already iota gamma some index delta some index psi, and that index is being summed over, should be equal to m psi. So using this equation of motion, the second term will become m square psi. Okay, while the first term I have a gamma alpha gamma mu and the two partial derivatives. Now you can see that what I can do, this alpha is also summed over, mu is also summed over. Alpha are going to take value 0, 1, 2, 3, mu is also going to take value 0, 1, 2, 3. So that means I can write it in a nice way, that it is gamma alpha gamma mu del alpha del mu plus 1/2 of this. The same thing again, gamma alpha gamma mu del alpha del mu. The same thing I can write, right? Where alpha and mu's are being summed over. Now in the second term, I can do a relabeling. So alpha is being summed over, gamma alpha gamma mu, and del alpha del mu is there. So what I can see, both alpha and mu are being summed over. So it doesn't matter, this has to take value 0, 1, 2, 3, and mu also has to take value 0, 1, 2, 3. So it doesn't matter whatever I call what. So I can call for alpha, replace alpha with mu and mu with alpha. So this will become mu and this will become alpha. This will become mu and this will become alpha. However, the partial derivatives, as we discussed, commute with each other. So I can write it back as del alpha del mu. First I converted mu into alpha, then the roles of mu and alpha get flipped off. But this first two gamma matrices cannot be brought back in the previous form because they do not commute, but partial derivatives commute. So I can write down del alpha del mu del alpha, which was appearing again back as del alpha del mu. So therefore I will get a structure half times gamma alpha gamma mu and then gamma mu gamma alpha, both coming with del alpha del mu, which is the anti-commutator of gamma alpha gamma mu. So see this thing with clarity. First, what I did, I just wrote it into half of twice of its pieces, and in one of the pieces I made use of the fact that this partial derivatives commute. Therefore, I can write the whole term as this. You can verify the whole term appearing over here is the same as this. Okay, you can just open it up, gamma alpha gamma mu plus gamma mu gamma alpha, and do the summation. So that means here alpha and mu summation is implied, and here also alpha and mu summation is implied. Do these things, obtain what are the terms you are getting, do this thing, obtain all the terms you are getting, you will see that both the terms are the same. So therefore I can write the term which is appearing over here is as gamma alpha gamma mu anti-commutator and del alpha del mu of the psi. Now I also know that the anti-commutator of gamma mu gamma nu, that means gamma alpha gamma mu, is minus twice of the Minkowski metric eta mu nu. So that means this can be written as a minus of eta alpha mu, and alpha and mu are being summed over. So that means summation over alpha mu is implied. And now you see this is nothing but the Klein-Gordon equation. So therefore the Dirac equation which we obtained as a solution of a Dirac equation of motion also satisfies the Klein-Gordon equation. Okay, this is not a mystery because the second order Klein-Gordon equation is the unique solution which is Lorentz invariant. So therefore its second derivative version should better satisfy the Klein-Gordon equation as well. So therefore the solution which we have obtained for the Dirac equation is a solution to a harmonic oscillator structure as well. So psi is like a harmonic oscillator again as well. So therefore we can employ, right now it is not a harmonic oscillator, it is Klein-Gordon, but going to Fourier basis it will become harmonic oscillator equation for different k basis as we had done for harmonic, the scalar field. So therefore this can be converted back into harmonic oscillator like structure, and therefore the usual quantization scheme which we adopt for a scalar field, which is quantization of oscillators in Fourier space, can be adopted here as well. So I know the solution of harmonic oscillators. I can write down those as the operators and then quantize the full field, and that is what we can do for the spinor field as well. In the next class we will try to see how to do this for a spinor field. The usual way looks very much settled, that we can do it the way scalar field was done because both of them satisfy the same equation, and we know it has a richer matrix structure. Scalar field was just a number. This time we have 4×1 matrix. That means it has different components. All the components satisfy the Klein-Gordon equation. So therefore it is a collection of more oscillators. Spinors is collection of more oscillators. So we can quantize it like we quantize an oscillator, and that is what we will do in the next class.